So sometimes when doing problems with a Poisson distribution, it's necessary to calculate the sum over all possible x values, as x goes from some number to infinity. You've probably noticed this in a couple of your homework problems. So I thought I would do an example here with actually how we can calculate the mean and the variance of the Poisson distribution from first principles, calculating expected value of x, calculating expected value for x squared, if you will, and do this directly rather than do it with a moment generating function like we did in class. So in this problem, when we have the expected value of x, that's our mean, of course, we're going to sum over the support. So our support here is from 0 to infinity. And then we do x times the PDF. And this, of course, is our PDF for the Poisson distribution. So what we notice first is that if I plug in 0 for x, I'm certainly going to get 0. So I might as well start this sum at 1. So I have the sum from x equals 1 to infinity of the same summand. All right, so notice that this x here will cancel with one of them on bottom. So I can cancel the x's and get the sum from 1 to infinity of e to the minus lambda, lambda to the x on top, but an x minus 1 factorial on bottom. Next, I'm going to factor out some pieces so that I can make the exponent look like what's in the denominator here for the factorial. So factor out a lambda, and of course I can factor out an e to the minus lambda because that has no x's in it. And now I'm left with a sum from x equals 1 to infinity of lambda to the x minus 1 over x minus 1 factorial. Now, if I re-index, notice that, in particular, if I plug in 1, really this sum starts at 0, right? If we plug in 1, we get lambda to the 0 over 0 factorial. And then if I plug in 2, I would get lambda over 1 factorial, and so on up the line. So I might as well just start this sum at x equal to 0 and replace our x minus 1s with x's. I get the exact same sum. The benefit of this is because now I can recognize what this sum is. That is our summation formula for e to the lambda. We have that for our Maclaurin series for e to the x in general, and I've plugged in lambda for the x value. So now I've got lambda e to the minus lambda times e to the lambda, and then of course these two pieces will give me 1, so I get lambda. So this is a way again to show that the expected value for the Poisson distribution is lambda. We can do something similar for the variance. Now, in general, we typically compute expected value of x squared times minus expected value of x quantity squared when we do the variance formula. However, in this case, it's a little bit easier to start with expected value of x times x minus 1. Notice there's an expected value of x squared in here. I've got x squared, and then I've got a minus what will be expected value of x. We'll talk about that here in a minute. But let's see why this calculation is beneficial for us. All right, so same idea. Take the function that we're trying to find the expected value of, multiply it by the PDF. Here I notice that if I plug in 0 and if I plug in 1, I get 0 for the summand, so I might as well start it at 2. We can cancel an x and an x minus 1 with the x factorial on bottom, leaves us with x minus 2 factorial with the same numerator, e to the minus lambda, lambda to the x. Now we're going to do the same kind of trick that we did in the previous part. I want this exponent to match this expression in the bottom. So to do that, I need to factor out a lambda squared out in front. I can still pull the e to the minus lambda also out in front because there's no x's. Now I'm left with lambda to the x minus 2 over x minus 2 factorial. Now, much like what we did in the previous example, if I plug in 2, notice this really starts at 0. So I've got lambda to the 0 over 0 factorial. If I plug in 3, I get lambda to the first over 1 factorial, and so on up the line. So I might as well re-index this to start at 0 and replace the x minus 2's with x's. Then same idea as what we had last time. This part right here sums up to e to the minus lambda. And then if we simplify e to the minus lambda times e to the lambda, we just get lambda squared. Now this is not the variance. This is the expected value of x times x minus 1. So to calculate the variance now, we notice, remember, variance we can calculate as expected value of x squared minus expected value of x quantity squared. Here, if I multiply this through, we get expected value of x squared, but I also get a minus expected value of x. So I need to add it back in order to be able to cancel it out and have our variance formula. But now I just plug in the values. We calculated this as lambda squared, and we know that expected value of x we did in the first slide. That's a lambda, so I get lambda squared plus lambda minus lambda squared gives us lambda. So that also derives our variance for Poisson, which we also recognized from our moment generating function discussion before. So anyway, the point of this was to show you how you can calculate these expected values using the summation formulas and recognizing that you have an e to the essentially lambda as a piece that you've added up.